As developers, we often encounter situations where the content we want to display on a desktop application is larger than the window itself. This is where scrolling comes in handy, allowing users to view the entire content by simply moving the scrollbar. In this tutorial, we'll take a closer look at scrolling in wxWidgets. We'll start by using the wxScrolled template with sizers to add scrollbars automatically to your application. Then we'll add content scrolling for controls that have absolute positions. Next, we'll build a bitmap viewer control with scrolling and zooming capabilities. Finally, we'll create a zoomable canvas where the user can place, move and rotate graphical objects, and demonstrate how to handle mouse events on scrolled windows. As always, our examples will work on all three major operating systems without any code changes. So whether you are a seasoned wxWidgets developer or just starting out, this tutorial is for you. By the end, you'll have a solid understanding of scrollbars in wxWidgets and be able to add this important feature to your desktop applications. Let's get started. We start with a basic wxWidgets application containing an app object and the main frame. The code for this tutorial, including the whole CMake build configuration that automatically downloads wxWidgets sources if needed, is available in the GitHub repository. Check the link in the video description. We add a simple panel and a vertical sizer. Then we add several buttons in the loop so that they overflow the window. Next, we set the sizer and run the app. With this setup, the user can't see all the buttons. To go past button 5, we need to resize the window. To fix this, we introduce scrolling in the simplest way possible. We wrap our panel in the wxScrolled template and set the scroll rate: 0 in the horizontal direction, meaning no scrolling, and 10 in the vertical direction. The actual value is important for systems that have scrollbars with arrows. On Mac, it does not change the behavior. We can scroll the content using the mouse wheel by grabbing the scrollbar thumb or clicking the scrollbar area. The app looks native on every operating system. On Windows, we get the arrows that scroll the content by the amount specified in the set scroll rate call. Similarly, on Linux, we get the native GTK look and feel. If we don't use sizers but still want the ability to scroll the content containing some controls, we need to provide more information. Here we built a simple checkerboard using absolute positioning. To draw the squares, we used colored panels. To better see the scrolling effects, we add the ability to change the square colors with a mouse click. Here's how this looks like without any scrolling capabilities. As before, the user needs to resize the window to reveal the entire content. To enable the scrollbars, we again wrap the panel in the wxScroll template and provide the information needed to calculate the scrolling, the scroll rate, just like in the buttons example, and the virtual size. Now we can scroll and reveal the hidden parts of the content. Let's move on to the bitmap example. Here's a simple bitmap control that displays an image centered but not scaled. We have a basic onPaint handler and some methods to update the bitmap. I recommend my custom controls video if you want to know more about creating custom controls and drawing with the graphics context. We include the bitmap header in the main file and add the control as a class member. The onOpenImage method will open the file dialog where the user can choose the image to be displayed. Update bitmap is just a helper method to update the control with the new picture and refresh it. We init the image handlers and proceed to build the UI. This is the usual stuff: create the controls, bind the callbacks, and add to sizers. For more information, check out my basic layout tutorial. Here in the button click callback, we open the file dialog, allowing only the image file types. We won't be talking about the details of dialogs in wxWidgets in this tutorial, but be sure to check my dialogs video if you are interested. We finish with the update bitmap image method and run the app. Here we load a large image that does not fit the screen. The only way to see more is to resize the window. This application definitely needs some scrolling and zooming capabilities. By the way, remember to subscribe to stay updated on the future videos, and give this one a like if you're enjoying it so far. Note that our class derives from wxScrolled wxWindow, not just wxWindow. This is the first thing that needs to be set to enable scrolling. We introduce the zoom factor to zoom in or out by 10%. The zoom level indicates how many levels we moved from the initial 100%. So to get the scale factor, we need to multiply or divide the zoom factor itself that many times. Or in other words, use exponentiation. We use this scale factor or zoom multiplier for calculating the scaled bitmap size. This method will be helpful in two areas. First, we need to increase the virtual size to match the scaled bitmap, and we do that with the zoom in and zoom out methods. Setting virtual size also has to happen when first loading the bitmap to enable scrolling. The second place which requires a call to get scaled bitmap size is the onPaint method. But before we do that, we need to explain the doPrepareDC call. The device context origin is by default at the upper left corner of the client area of our control, and that's where all drawing begins. Since the scrollbars have moved, we cannot draw starting from this point, and we need to move our device origin up and to the left. That's precisely what doPrepareDC does, so the 00 point is adjusted after that call. Now drawing starts from there, and our bitmap looks shifted as if it has been moved by the scrollbars, which is what we expect. Finally, we use the correct sizes in the drawing code. Now the bitmap will be scaled thanks to the draw bitmap call. Moving on to the main file, we add the buttons and callbacks for the zoom actions so that the user can change the zoom level. The button click callbacks themselves are really simple, just calling the appropriate methods from the bitmap class. We load our large image and start experimenting with the app. The scrolling works great, and the zoom buttons correctly change the size of our bitmap. If you look closely, however, you can notice something weird. When zooming in, our image moves toward the top left corner, while decreasing the zoom level tends to move in the opposite direction. A better way to implement this behavior would be to keep the center of the visible part of the image roughly in the same spot. This will provide a more stable and intuitive experience for the user, as their point of focus remains centered and unchanged. Let's add a method that does this. The parameters will indicate the position of the visible view center before and after the zoom happens, and these positions will be relative to the image origin. Because of this, we can calculate the delta vector and scroll so that the new center is at the same position in the window as the previous center was. Here's our view center before zooming, and this is where the center should be after zooming. We calculate the delta vector, scroll back, and end up with an enlarged and centered image. But how do we calculate these center positions? To get the view center before scrolling, we use the built-in calc_unscrolled position method, which returns the given position relative to the origin of the scrollable content. In our case, the scrollable content is the image, so if we provide the center of the viewport, the method will return how far the pixels in the center of the viewport are from the 0,0 point of the image. What about these pixels after the zoom? To get their offset from the image's origin, we multiply the current center by the scale step. We do the same for the zoom out procedure. This time, however, to get the center position after zoom, we need to divide the coordinates by the scale step. Since the wx size does not override the division operator, we multiply it by the inverse instead of dividing, which mathematically is the same. After running the app and loading the image, we scroll a bit and experiment with zooming. As you can see, we keep the center of the viewport as the focal point, making the scaling operations look smooth and intuitive. And this is how it looks on Windows. Nice and smooth as before. You may wonder though, why we use this particular order of operations. Why first scroll and then set the virtual size? While the order should be irrelevant, the reverse order, where we first set the size and then scroll, seems more natural. The thing is, on Windows that particular order causes problems. If we run the app with the changed order, load an image, and try to zoom in and zoom out, we see that the scroll bar thumbs start to jump around, making the experience much less smooth than before. Unfortunately, this is a known bug in the library. For now, the workaround is to use the reverse order. First scroll and then change the virtual size. Let's move on to something even more complex. This time we'll take the rectangles example from my custom controls tutorial and improve it by adding the clipping canvas, scrolling capabilities, and zooming. This interactive example allows the user to move and rotate the objects, so we will have to take that into consideration and make sure our mouse events are handled correctly, regardless of the scroll position and zoom level. Here's the initial code. We have an object structure representing a single rectangle. Then there is a custom control named Drawing Canvas, where the objects are rendered and the user interactions take place. Throughout the code, we make use of affine transforms quite extensively. Whether it's drawing, hit testing, or moving or rotating the objects, the transforms are there. If you are unfamiliar with the concept, I recommend my custom controls video, where I go to great lengths to explain how that works. The Drawing Canvas CPP file is also added to the CMake list in the Sources section. The main CPP file is much simpler than the custom control class. There we handle the UI construction and generate random positions for new rectangles. And here's how this looks like. We can move the rectangles by clicking and dragging, and rotate them by clicking while holding the Alt key. Unfortunately, there is no way to get the rectangles outside the client area, and there is no zooming. Let's change that. First, we'll introduce a canvas to place the rectangles. It will have constant dimensions, but the users will be able to zoom and scroll through it. We'll also ensure that the random position generator does not place the rectangles outside the canvas. Before we draw the canvas, we'll fill the visible control area with gray color to make the canvas stand out on systems with light color themes. We choose the right color and fill the control area using the System Settings object. For the canvas, we use white color. Before we draw the canvas, we use the clip method to ensure that nothing gets drawn outside. Then we draw the white rectangle and bring back the transparent pen so that the rectangles drawn in the following loop do not have a white outline. This looks good. The Add Rect button does not generate any rectangles outside the white area, and the rectangles inside are correctly clipped. We definitely need scrolling now, so let's implement it. As always, we wrap our control in the wxScrolled template. Then we set the scroll rate to 5 pixels and use the canvas bounds to calculate the virtual size. We increase that size 2 times by the canvas offset to get the margins in all 4 directions. Like in the bitmap example, we call doPrepareDC in the paint handler to automatically change the drawing origin depending on the scroll position. Lastly, we make sure the gray background covers the full scrollable content using getVirtualSize. With these simple changes, we now have scrolling in our application, but there is a problem. If we scroll a bit and try to move the rectangles, we get weird behavior. That's because we still need to consider the scroll offset in our mouse event handlers. We'll fix that shortly, but first, let's implement zooming. The approach is the same as with the bitmap control. There is a zoom factor, zoom level, and methods to adjust it. The Scale Transform Helper method will be useful both for drawing the rectangles and fixing the mouse hit tests later. We move the code from the constructor to the separate method, as we will need it in more than one place. Also, we now have to consider the scale when calculating the virtual size, and we do that by multiplying the size and margins by the scale factor. The Scale Transform method takes a transform and applies scaling by the current zoom multiplier. We'll see in a moment how to use this method. In the onPaint handler, we scale the canvas, and then for every rectangle, we alter their transform by adding scaling. As a result, a rectangle will not only be translated and rotated, as a result of the user's actions, but also scaled, reflecting the current zoom level. Note that when combining affine transforms like this, the order of the operations is crucial. Again, I recommend my custom controls tutorial, where I explain that in detail. Next come the zoom buttons in the main CPP file. Nothing fancy here, we just add simple buttons with callbacks and run the app. Zooming seems to work. There is no centering, and we'll fix that at the end, but before doing that, let's take a closer look at mouse events. As you can see, the interactions with the rectangles look weird. I'm able to click an empty space and move the rectangle. Also, the rectangle moves faster than the mouse pointer when dragging. Let's fix those, starting with the hit test issue. Here's the mouse click handler performing hit tests. To check whether the user clicked inside the rectangle, we take the mouse coordinates and convert them to the object's coordinate system using the inverse of its affine transform. Again, if that needs to be clarified, remember to check my custom controls tutorial. We need to update that transform with the current zoom scale, and the hit tests will work correctly. Now the issue with dragging and the rectangle not following the mouse pointer. Again, we need to alter the object transform, this time when calculating the drag offset. Finally, the rotations. When zoomed, the rectangle rotates relatively fast, and it would be more natural to allow greater rotation precision when working on zoomed canvas. To implement this, we divide the rotation amount by the current scale. This looks good, except when we scroll. We are back to square one with our hit test problems. Clicking the white area selects some random rectangle. Definitely not what the users expect. We need to introduce another transform modifier, this time to compensate for the scroll offset. The code is similar to the previous one, but we add a translation this time. The calc unscrolled position gives us the offset of the viewport origin from the origin of the scrollable content, and we then negate these values to reverse the effects of scrolling. You may think of this transformation as a means of calculating the position of an item on the canvas relative to the viewport area. Since the mouse event coordinates we use are also relative to the viewport's origin, we only need to apply this method to the object's transform in our mouse click handler. Now, no matter where we scroll or how much we zoom, all the mouse events work correctly. The last thing to fix is the centering after zoom, so let's do that now. This is precisely the same as in the bitmap example. We calculate the current viewport center relative to the content origin, change the zoom level, and scroll back to the previous center, scaled by the zoom factor. We use the same center after zoom method for calculating the offset and scrolling, taking into consideration the current scroll rate. So that's it for this tutorial. We started with elementary examples and ended with a quite complex custom control that not only implements smooth zoom and scroll, but also correctly handles the mouse events. I hope that was useful. Remember to like and subscribe, and I will see you in the next one.